Hello everyone. Welcome back to the last session of AI Summer School. I am Devashri. Today, me and my fellow coordinator Anirudh will be taking a session on NLP, Natural Language Processing. I will be covering the basics of NLP and word embeddings, and Anirudh will delve into the idea and working of RNNs and LSTMs. Okay, so we'll get started. Right. Okay, natural language processing. Okay, so first, before I start the session, I'll go through what are we going to cover in the next 1 hour. First, I'll be introducing you to NLP and give a brief, give an intuition of what NLP is, and then I'll mention a few real life applications of NLP. And then we'll cover one of the most crucial and important part of any NLP application in real life, that is text pre-processing. Then we'll learn about word embeddings and the different types and representations of word embeddings. The following, okay? Yes. Okay, so before I talk anything, just take a look at the Venn diagram over here. This is a beautiful representation of NLP. So it is the intersection of computer science, artificial intelligence, and human languages. Okay, so computers they usually work with structured data like tables, CSV files, and spreadsheets, unlike us humans, where we have a variety of languages, accents, and tones for communication, which the computers cannot interpret. So, NLP, the main objective of NLP is to process this unstructured data and retrieve meaningful information out of it using artificial intelligence, with the help of artificial intelligence. Okay, so these are the applications. You might not really realize, but you actually use a lot of you might use a lot of applications that are trained based on NLP and NLP models. So let's have a look. So firstly, sentiment analysis. Sentiment analysis is to classify the emotional intent of the text. So text here can be, say, reviews or comments. Reviews of a movie you want to watch, or comments for comments and reviews again for, say, an Amazon product, which I'm sure we all might have come across at some point. So the output is so it takes all these reviews and comments as the input, and the output is the probability that the sentiment expressed is either positive, negative, or neutral. So instead of reading through all the comments or reviews, it would make your life easier to actually see what percentage of the comments or reviews are positive, negative, or neutral, which will give you a good understanding of whether the product is good or bad, whether you can buy it, or whether it is advisable to watch the movie or not. Okay. The second is grammatical error correction. Grammatical error correction models, they are such as Grammarly. We all might have used Grammarly, or even say Microsoft Word, which automatically corrects your grammatical errors. They are trained based on grammatical rules, that is grammatically correct text. So it takes in input. So it takes the text which you're giving as the input, and it will output a word, or if based on the rules it has learned, the grammatical rules. Right, spam detection. Okay, so I'm sure college students here would relate very much to spam detection, and how you would realize how important it is to filter out all the spam and irrelevant mails that you get in your college mail. So spam detectors, they Their main aim is to output the probability that a given mail is spam or not. So it takes input such as some parts of the text, like a few words or phrases, which it might need to find in the mail to classify it as spam or the sender's email ID, etc. Yeah, other applications also involve chatbots and search engines. So chatbots for summarization, text generation, conversation generation, and search engines, they understand our the natural language query, which is not a very structured format. We might use different for there are different ways of asking the same question. So search engines also are trained on NLP models to understand. Okay, so first we'll get into the most crucial part of NLP, the most initial and crucial part of NLP, that is text pre-processing. Text pre-processing is very crucial initial step of NLP. So it is basically clearing and transforming the unstructured data to prepare it for analysis to be given as input to the machine learning algorithm. Okay, so you'll understand this better when we see what are the steps involved in text pre-processing. Right. Firstly, noise removal. Noise in text refers to all the irrelevant and redundant characters or information that which is not required for the model to actually understand anything. The various ways of removing noise include removing punctuation, removing special characters, removing numbers, removing HTML tags, and HTML formatting. Here. Right. Lowercase. Next is lowercase. Lowercasing is simply converting all the text we have to lowercase. So this is important to standardize the text we have. Okay, for example, we have a text which has mixed case occurrences of the word Canada. So there are, for example, say in the text, there are two occurrences of the word Canada with a capitalized C and the second with a lowercase c. So in this case, that is a step called tokenization, where all the unique words are, for example, consider there is a vocabulary which all the unique words of the text. It contains all the unique Okay. Hello, guys. There was a small, yeah, I got muted. So I'll just start the presentation again. So I didn't realize when I got muted. Okay. So NLP. Okay. So first I'll take you through the contents of what all we'll be learning in NLP. First, I'll give you the introduction, then the applications of NLP. Next, text pre-processing, which is one of the most crucial step in text pre-processing. in NLP for any real based NLP model. Okay, next is word embeddings. I'll give you a brief introduction to word embeddings and the different types and representation of word embeddings, the corresponding ones. Okay, so introduction. So before I explain anything about NLP, this Venn diagram right here, just take a look here. So this is a beautiful representation of what NLP is. It is a intersection of computer science, artificial intelligence, and human languages. Okay, so computers as such they work with structured data such as tables, spreadsheets, CSV files, whereas we humans communicate in various languages, accents, and tones, which the computers cannot interpret. So the main objective of NLP is to make the computers understand this unstructured data, the unstructured text which we input, and retrieve meaningful information out of it. Right. So even you might not even realize that you're using NLP based models or NLP applications in your real life world. Let's see some of them. So first is sentiment analysis. Sentiment analysis is the process of classifying the emotional intent of the text. So the text, as in say reviews or comments. So reviews for like say movies, comments for any Amazon product you want to buy online. Okay, so this outputs the probability of a comment or review, the text being either positive, neutral, or negative. So the input is all the reviews and the comments, and the output is a probability that either it's positive, negative, or neutral. So instead of reading all the reviews or comments, you can see what percentage of the comments are positive, negative, or neutral, and hence you can, it will save you time. Like you can decide if this is a good movie to watch or if you can really buy that product. Okay. Second one is grammatical error correction. So grammatical error correction models, they're based on, they're trained on grammatical rules. The text that contains grammatically correct text. So it takes the input, the typed text that we put in, and it outputs a phrase or a word that is grammatically correct after it. So it's a sequence to sequence task. We come across this not only Grammarly, we also come across this in Word, Google Docs we use. Right. Okay. Spam detection. So the college students, I'm sure, will very much relate to this. It becomes very essential to actually filter out all the unwanted and irrelevant mails that we do not require. So spam detectors take and input the mails along with some text, such as the words the words which might be contained in the spam mails, and say the sender's email ID, and it outputs the probability that the mail is either spam or not. Other applications are chatbots, search engines. Chatbots we commonly use for summarization, text generation, conversation generation, right? And then search engines, they are designed to understand our natural language query, which because there might be different ways of asking the same question. So it's trained based on an NLP model. Okay. So text preprocessing. Text preprocessing is one of the most initial and crucial step for any NLP application. Okay, so text processing simply means cleaning and transforming the unstructured data we have to prepare it for analysis, to input it to the ML algorithms. So if we look through the steps, and it'll be more easier to understand what pre-processing. Okay, first thing is removing noise. Noise in text refers to the irrelevant information or characters that might be contained in the text, which is not really required for the ML algorithms to learn anything out of it. Such as, so the different ways to remove noise in the text include the removal of punctuation, special characters, numbers, HTML tags, etc. Okay, next is lowercasing. Lowercasing, it simply involves converting all the text present to lowercase. So lowercasing is important to standardize the text. For example, we have a text which has mixed case occurrences of the word Canada. So one with a capital C and one with a lowercase c. So if we consider a vocabulary with all the unique words of the text, so it will consider Canada with the capital IC and Canada with the lowercase c as two different words. Okay, so and this is not desirable. So maybe for a small text, for a small paragraph, it doesn't make much difference. But for large amounts of data, it generates a large amount of redundant words in the vocabulary, which is undesirable and it makes it computationally inefficient. So we perform lowercasing to reduce the vocabulary size. Right. Next, tokenization is one of the key step of text preprocessing. So tokenization simply means breaking the text into smaller units, breaking the sentences into smaller units. So in this case, if you have a text, the simplest unit of the text, you can think of it as a word. So tokenizing the given text into words is the most common tokenization process, also known as the white space tokenization. Other tokenizations also include sentence tokenization, where each token corresponds to a sentence instead of words. Okay, so here the text represents a meaningful unit, the smallest unit which has meaningful information that can be used by the models to extract meaningful information out of it. Okay, so here, as you can see in the example, natural language processing, let's say it's like a word. And then when you tokenize that, it returns a list with each of the words as its elements. Right. Yeah. Now, removal of stop words. So stop words are the words that do not add much information to the text on their own, and they occur very often. For example, say common words like in, is, an, the, you, me. All these words, they occur pretty often in a given text and they do not add much meaning to the text on their own. So we would like to get rid of this and filter these words out. Okay, see, for example, we in the search engine, we search what is text preprocessing. So in this case, we would want to focus more on the term text preprocessing rather than what is. So in this case, what and is can be considered as stop words. Okay, so and one warning I would like to give here for stop words is every NLP application has a different set or vocabulary of stop words. For example, usually stop words, all the prepositions, determiners, all these can be articles. They can be considered as stop words. But in some applications like sentiment analysis, let's say, the token not, if you remove the token not from the text used for sentiment analysis, it changes the entire meaning of the review or the comment. So you would not want to do this. So care must be taken before using the vocabulary or the step or the set of stop words you want to use for a particular application. Right. Yes. Part of speech tagging. So in part of speech tagging, it's pretty self-explanatory. You would want to tag each of the word in the text according to its part of speech. Okay. The main objective of doing this is because you would want it to understand the context of the word in the given text or given the sentence. For example, say there are two sentences. I want to buy an Apple phone. And the other sentence is, I like to eat an apple. So in these two cases, the word apple has different context. In first case, it's a proper noun. And in the second case, it refers to a fruit. Okay, so by using POS tagging, it can actually understand the context of that word. And it can understand the context of that word and give more information to the model when it is training. So here, here it's mentioned in NLTK. So NLTK is a natural language toolkit, is a built-in Python library for NLP. It is the most common and widely used NLP library in Python. So this is there are built-in libraries to perform POS tagging. So for example, if this is the sentence tagging. So the tag, if it deals with, so for different parts of speech, these are the tags which it starts with. You don't really have to know this. Just to give an example over here, I have displayed the table over here. You don't have to know this. This is just for the conceptual understanding. Yeah, normalization. Now, normalization of text refers to converting each of the words, or say tokens, to its most basic form, converting the words to its base word. Okay, let's see, why are we supposed to do this? For example, in a text, let's say there are words like change, changed, changing, and changes. So all these words have similar meaning. But instead of having all these words in the vocabulary, it would be preferred to have one word that can replace all these words but convey the same meaning. So, which basically refers to the root word or the base word of all these words. That is change in this case. So instead of having all these words like change, changed, changing, changes, all these in the vocabulary, we can have only the word change in the vocabulary. So yeah, so this will automatically reduce the total number of unique tokens and also reduce the redundant data, which in turn reduces the data dimensionality. Okay, so there are two techniques of performing normalization. One is stemming and one is lemmatization. Okay, stemming involves removing suffixes from the words, whereas lemmatization involves converting the words to its grammatically correct base word. Okay, so look at the example of here on the left. So in this case, for improve, improving, improvements, improved, improver, it has just removed the suffix over here, and the common word from all this will be improve without the E. So this is the output of all these words after stemming. Whereas in this case, you can see this is the example of lemmatization. So here the output will be improve. The grammatically correct word here, improve. Right. So in stemming involves simple algorithms to just remove the suffixes. But for lemmatization, it has to have a linguistic and grammatical understanding of the language to perform lemmatization for a given set of words. Yeah, the features of stemming and lemmatization are mentioned here. Stemming is simpler and faster. But sometimes it can lead to a base word which is grammatically incorrect, as we've seen in the previous case, which leads to ambiguity. But lemmatization is a more accurate and grammatically correct. It results in a grammatically correct word, but it is more complex. It is slower technique. Okay, let's see in what cases stemming can be applied and in what lemmatization can be applied. So stemming can be used in cases where the given output after stemming is the meaning of the word is not important. For example, say spam detection. For spam detection, you just have to identify that piece of the word in the given mail, in the given spam. So it need not understand the meaning of that word, whereas a lemmatization would be required where the meaning of the word is important, say in chatbots for text generation, summarization, or conversation generation, right? Okay, so this time I'll present you a Slido question. So everyone scan this QR. I will start the quiz in about a minute. Make sure everyone scan the QR. Okay, I'll be starting the poll. Yeah. Go ahead. Answer. This requires reading all the options, so I'll be giving 1 more minute. Okay. Yes. Yeah. So, as most of you have answered, the first option is correct. Lemmatization requires more linguistic knowledge than stemming because it has to convert it to a more grammatically correct word. The rest of the options are wrong. Stemming is more accurate than lemmatization. No, because stemming outputs a word which might not be grammatically correct as well. Stemming and lemmatization cannot be used interchangeably. They surely have varied applications, different applications. Lemmatization is faster than stemming? No. Stemming involves simple algorithms to just remove the suffix. So stemming is faster than lemmatization. Sure. Okay, I'll be stopping the poll. Okay. So we'll move on. Okay. Word embeddings. So word embeddings are numerical or a vectorical representation of the tokens which we have generated in text preprocessing. Okay, so yeah, they are vectorical or numerical representation. We convert the tokens into numbers or vectors because computers or ML models, they're more comfortable with working with numerical data than working with string data or text data. So it will be easier for the models to extract features from the numerical data. So hence word embeddings is an essential part of NLP. Okay, so on this point right here, it allows words with similar meanings to have similar representation. This will make more sense when I will further explain the different representations of word embeddings. Okay, the first one is bag of words. So bag of words is the simplest form of numerical representation of sentences. I can say here, it's not for a word, it's for a sentence. Okay, so what does bag of words involve? So this basically involves converting the given text or a set of sentences into vectors which represent the frequency of the words, which represents the frequency of the word. So, and in this case, it does not consider the order of the word. So let's take an example, then it'll be much more easier to understand. Okay, so let's take, these are the 3 reviews for some movie. Okay, so these 3 other reviews. So first review is the movie is very scary and long. Second is the movie is not scary and is low. The third one, the movie is spooky and good. So these are the 3 different reviews. So we need to, our aim is to find the word embedding or the numerical representation of these reviews. Okay, so for that, firstly, we'll build a vocabulary from these 3 given reviews. So to build a vocabulary, we need to consider all the unique words from the above all the reviews. Okay, so there are 11 unique words, namely, this movie is very scary and long, not slow, spooky, good. So these are the all the unique words. Okay, so now for to create the matrix, I've plotted a table, put a table. So in this table, the rows consist of the reviews and the columns consist of the words. So in the table, you mark, uh, you fill in the values with zeros, ones, and two, or with the frequency of the number of times these words occur in the particular review. So, for example, in the first review was this movie is very scary and long. So here for the word this, there is one. So for movie, there is it's represented as one, is one, very scary and long. So these are all zero because these words do not occur in review one. Similarly, for review 2 and 3, so for review 2, it goes like this movie is not scary and is long, right? So, and this is the review 3. So corresponding to these reviews, the frequency is marked in the corresponding cells, and these values right here is just encoded into a matrix over here. So this is the bag of words matrix, a very simple representation of word embedding right here. But there are few limitations to this approach. Firstly, no word order. See, it doesn't care about the order of the words, because if, for example, say the words were jumbled in the given sentence, it would still output the same matrix. So it doesn't take into consideration if the given review is in the grammatically correct order or not. Secondly, it ignores the context. It doesn't understand the meaning of the given words based on the words around it. For example, as I had told you in one example I told you in the previous case. So I like eating an apple, and I want to buy an apple phone. So in these cases, the word apple has different context in the two cases. But in this case, it doesn't take that into consideration and it ignores the context. The third one, it is again computationally inefficient, because if the data contains a large amount of text, then the set of vocabulary will contain a large number of unique words. And for one particular review, there'll be a lot of zeros, and it will make it computationally complex. So this is inefficient, and it's not advisable to use this for large amounts of data. Hence, a new form of word embedding was introduced, that is TF-IDF, term frequency inverse document frequency. This is not exactly a representation, a numerical representation of the given word. Rather, it is a numerical statistic which actually shows how important that word is in a collection of documents. So a collection of documents is also called a corpus. So it reflects how important the word is in the corpus. So before we understand its significance, so let's see what these individual terms are. So TF-IDF score is calculated as TF into IDF, and these are the formulas for TF and IDF. So TF is equal to number of times a word appears in a document divided by the total number of words in the document. So it is essentially the frequency of that word, rather the scale frequency of that word, because frequency would just be the number of times it occurs in the document. Scale is because it is divided by the total number of words. IDF is log of total number of documents divided by the number of documents with the word in it. Okay, so this formula will understand the significance of it when we come to the features. Okay. So what does TF measure? So TF measures how frequently the word appears in a document. So a higher TF value means that that word is more significant in the context of that document. Okay, and IDF measures how rare the term is across the corpus. So let's see how. For example, the words such as the, and, is might occur in all the documents, more or less. It appears in all the documents, and many number of times it occurs very commonly. So for that, the TF term will be pretty high. Right. It'll be very close to 1. And let's see what happens to the IDF term. IDF term will be log of total number of documents divided by the number of documents with the term T in it. For example, let's take the word the. The might, let's assume that it occurs in all the documents we have. And it's very much possible, right? So, so this term right here will nearly be equal to the total number of documents. So log of 1. So this ratio will be equal to 1 or very close to 1. So log of 1 will be 0. So even though, so the TF-IDF score will be 1 into 0. So it'll be 0. So even though the word occurs very commonly in a document, even though its TF score is higher, but its IDF score will be less for terms that occur pretty often, which occur in almost all the documents. Right. So see the significance of TF-IDF. So this increases the weight of the terms that are frequent. So this increases the weight of the terms that are frequent in one document, but it is rare across the corpus. So if it is frequent in one document, but also occurs across almost all the documents, then its score will be very less again. So if it is frequent in one document and it is rare across all of the documents, then it makes it stand out as an important feature for that particular document. Right. The IDF component and also ensures that a few given words are given more weight. So in this case, TF term is the frequency, and the IDF term will be is essentially, you can think of it as the weight. Right. So this helps in capturing the contextual significance of the terms, because if a word is frequent in one document and rare across the corpus, that means that that word certainly has to do something with that document. It is telling you that, okay, this word belongs to only this document, and hence it explains something about that document and something unique about that document which other documents do not have. Okay, so let's take an example for better understanding of this. Okay, so let's say we have a corpus of three small documents. So document 1, the text is artificial intelligence is transforming technology. Document 2 is machine learning and artificial intelligence are subsets of technology. Document 3 is the technology in sports is improving rapidly. So now let's focus on the two terms, artificial and technology. Okay, so let's calculate the TF-IDF scores for artificial and technology. So in this table, I've calculated the TF scores for all of these, for both these words, and also the IDF scores for both these, and the TF-IDF scores for these. So one thing to note is that TF score for a particular word is different for different documents. For example, say for artificial, the TF scores might be different for, like, it is calculated for each document over here. Similarly, for technology, it is calculated for each document. This calculation is done based on the formula I showed before. Whereas IDF score is calculated only for a single, the IDF score is calculated only it is calculated for the entire corpus, for the entire collection of documents. So there'll be only one IDF value and not for each of the documents. So the corresponding TF-IDF scores will be the following by multiplying TF and IDF scores. So here, look at these values right here. Let's interpret something from these. So artificial receives a positive TF-IDF score in document 1 and 2, but 0 and 3. That means artificial has relative importance in documents 1 and 2, but not in 3. Right. Whereas technology receives TF-IDF score of 0 in all the documents, which means that technology is some topic which is common to all the documents, and it lacks the discriminative power. That means that technology cannot, the word technology cannot be used to distinguish any of these documents. For example, say artificial word can be used to distinguish document 1 and 2 from 3. So this has a positive TF-IDF score. Because technology lacks discriminative power, its value is 0 for all these documents. Right. So this was about, yeah. Now let's come to word-to-vec. So word-to-vec is one of the most interesting form of word embeddings, something which you can visualize more easily. Right. Word-to-vec allows the words to be represented as vectors in the 3-dimensional space, or any dimensional space in that sense, which you can visualize easily. So that there are 2 important features in case of word-to-vec, that is semantic representation and vector arithmetic. So firstly, semantic representation. So the words which are represented in the vector space, they are they're placed in the space such that words with similar meaning are placed close to each other. So that was the point again, which I told I'll come back to. So words with similar meaning are placed close to each other. That means the dot product of the 2 vectors with similar meaning is nearly 1. So that is the cosine rule, or the cosine explanation for that. So the words with similar meaning are placed close to each other, hence its dot product will be nearly equal to 1. The second is vector arithmetic. So in vector arithmetic, the words with the pair of words with same word relationships have the same vector. For example, in this image, you can see the vector from man to woman. So the man vector is from origin to this, and the women vector is from origin to this. So the man to woman vector is in this direction. Similarly, king to queen vector is in this direction. So this vector, you can say it represents the change of gender from male to female in this sense. Right. So this represents, so for a particular word relationship, it has the same vector. In this case, you can see walking to walked. So this word, word relationship represents present tense to past tense. Swimming to swam. These two have these are the same vectors essentially. Right. So for word-to-vec, there are 2 architectures which the word-to-vec uses to learn the word embedding. So these are the representations of it. But to actually learn these word embeddings, there are 2 architectures that is there. First one is CBOW, continuous bag of words, and the second is skipgram. Okay, so for a given text, the model loops over all the words that is present. And there are 2 things, so skipgram and CBOW. In skipgram, it takes a current word and it predicts its neighboring words. Whereas in CBOW, it takes the neighboring words and it predicts the current word. So let's see why it actually does the prediction. What is the entire point of prediction? Let's get into a little more detail. Okay, so CBOW architecture. Okay, so firstly, if I didn't mention, so CBOW and skipgram are 2 architectures which consist of neural networks. Okay, so CBOW, this predicts the target word given its context word. So when its surroundings words are given, it predicts the present word. So how is it done? So you give context window as a hyperparameter. You define that, say 1, 2, or 3. So context window is the number of words on either side of the given word you want to predict. So it takes it takes the context window as the input, and the words that are based on the given context window, it takes those words as the input, and it averages the word embeddings of all these context words. So these context words also have some word embeddings, word embedding representation. So it takes the average of all those word embeddings, and then predicts the target word based on this average vector. This average word embedding. Okay, so in this case, it is predicting that. Okay, so after I explain skipgram, I'll explain what is the entire point of prediction. So in skipgram, the objective is it will predict the context words for a given target word. So here again, it will take the context window as the hyperparameter. So in, for example, say here, this example, if it takes input as fox, its output must be quick, brown, jumps over. Not output, essentially, it should be able to predict the words around it, such as quick, brown, jumps, and over. This is effective for smaller data sets, because for large data sets, it becomes computationally inefficient and harder for the neural network to learn. So the entire point of performing these predictions is that it performs these predictions and it will compare it with what are the actual word embeddings of the target word. It calculates the loss function, and then it does back propagation, and then it optimizes the parameters of the neural networks, and hence the network learns after it is trained on large amounts of data, and then your word-to-vec word embeddings will be ready for use. Okay, so we're done with the theory. So we're done with the theory. Now we'll have a Slido quiz. Then I'll take up doubts if you guys have any, and then we'll move on to code implementation. Yes, so everyone scan this QR. I'll give you around a minute to scan, for everyone to scan the QR, and then I'll be starting the poll. Yes, I'll be starting the poll. This question involves one of the key concepts of the word-to-vec I had just explained. So let's see the results. Yes. Okay, as most of you have answered, man to woman as king to queen. This demonstrates the perfect word analogy in word embeddings. because, see, as I had explained, apple, orange. So these two vectors are placed close to each other because they have similar context or similar meaning. Cat and dog will be placed close to each other, and apple and orange will be placed close to each other. But there is no word relationship or anything in the sense for this case. Even here, sun, moon, tree, leaf, these two are somewhere related to each other. These two are related to each other, but there is no word relationship between these two. So even in this case, house and building have similar meaning. So they'll be placed close to each other in the vector space, and car and truck as well. They'll be placed close to each other. Okay, so here man to woman and king to queen is the answer, because this vector representation basically represents, as in the example, the change of gender from male to female. Yeah. So this concept should be pretty clear. Stop this. Okay, so before I move on to code implementation, let me take a few doubts. Yeah, see, the difference between skipgram and CBOW is mainly, see, these are two different architectures that are used to train the word to vec. So in one case, it takes a particular word if the text is input, and it predicts the surrounding words, whereas the other takes the surrounding words and it predicts the given word. So if the word to vec is either trained on either of these to learn the word embeddings for a given text that you give as input. So this is just a different method of learning the word embeddings. Both contain neural network architecture. So as I had mentioned, here I'll show it again. Right, so skipgram is not effective for small data sets. For larger data sets, CBOW is preferred because it has to predict only one word given the surrounding words. Hence, that's it. Yes, the collab notebook will be shortly shared. Yes. Okay. Okay, no more doubts? Do you guys have any other doubts? Okay, cool. Fine. I'll move on to code implementation. Okay, so the code implementation of this is pretty straightforward. There are built-in Python libraries for every possible thing that we can do. So code implementation is pretty simple and won't take much time. Okay, so firstly, data preprocessing in NLP. First, we need to install, and installing NLTK library is not necessary because in Google Colab, it's already installed. So we import the NLTK library. NLTK stands for Natural Language Toolkit. That is the most widely used NLP library offered by Python. So NLTK.download popular. So this popular contains a few data sets and the few functions it needs to perform. So we download this. Okay. So first, let's get some content. So I've taken this from a GitHub website. So this is the URL for that. I have taken, so I have downloaded the text from there. So text file is equal to open. So it reads this text. So when you run this, this text appears over here. It is uploaded to this Google Colab notebook in that way. So text is, it reads this text file. So when we print the data type of the text, so that is string, and this is the content. So to print the text, we just print the text. So this is the text that is printed. Once upon a time, there was an old mother pig, etc. So yeah, 3 lines over here. So firstly, we have the text ready now. So first, let's perform all the required steps of data preprocessing. So firstly, tokenization. Tokenize. So if we import the word tokenize function from NLTK, so words returns a list. So words is equal to word tokenized text. So it takes text as input and it returns a list where all the words are tokenized over here. As you can see, all the given words over here is tokenized from this. Next, from NLTK, import. So this is one form of tokenization, word tokenization, also known as the white space tokenization. The other is sentence tokenization. So this tokenizes each of the sentences. So each of the sentence corresponds to a token over here. So sentence is equal to sent tokenize of the text. Then you print this. So this is the list returned. Okay, now removing punctuation. So let's initiate an empty list to remove, to actually append all those characters which are not punctuation marks. So for W, so we run a for loop. For W in words, if W dot is alpha, so if it is a alpha numeric, so if it is an alphabet, then you append it to this list, right? Yeah, you also convert it to lowercase over here. So it performs two tasks essentially. It performs lowercasing and also removes punctuation. This one, right? So these are the words that do not contain the punctuation marks. So this is the list returned. And removal of stop words. So NLTK already has a given vocabulary or a set of stop words. So if you import that from nltk.corpus import stop words. So stop words dot words of English. So here you can also mention other languages. So we need English. So we mention English over here. So if we print all the stop words contained in the list stop words, so these are the ones, these are the words. As you can see, this usually occur very often in the text, in most of the text. So here we create initialize an empty list to add the words that are not contained in the list of stop words. So run a for loop for W in words, no punctuation, right? If W is not in the list of stop words, then you append it to this list. So that's what this does essentially, and you print all the words after filtering, after removing the stop words. So this is what we get. Okay, stemming. So yeah, stemming here. There are different functions that can perform stemming. So this is one of that function, that is Porter stemmer. There are also other types of stemmers. There are different stemmers based, and each stemmer has a given set of languages for which it is suited to. For example, this Porter stemmer is suited for English and might not work well with French for data which is contained in French language. So for English, this is the most preferred one. So we're using the Porter stemmer. So this is the word list. Let's say these are the words. We want to find its stemmed form. So study, studying, study, studied. So for each word in this list, porter.stem, if we perform, we get these words. So STUDI. So that's what it does. So this is the stemming process. Yes. So this is another example, NLTK.stem Porter stemmer. So studies, leaves, decrease, place. So for study, leave, as you can see, it just removes the suffixes, as you can see here. Okay. In case of lemmatization, the most commonly used function is the word net lemmatizer. So you initiate that function. Lemma is equal to word net lemmatizer. So for the same word list, you print the lemmatized form. POS tagging is equal to be. This basically means consider the verb form of that, the verb form of these words. So study is as it is, studying, studies, study. So the lemmatized form for all these is this itself, because you've given the POS tagging as the verb. So it considers the different verb forms as unique tokens here again. Right. In this case, you can see, you can even make out the difference here. Word list is equal to am, is, as, are, was, were. So when you lemmatize these, these for all these words, the lemmatized one will be B. Right. For am, B is this is the lemmatization. So hence it requires the linguistic and grammatical knowledge of the given language. Right. POS tagging. Yeah. POS tagging. So we have this as the sentence. Let's take an example of the sentence. A very beautiful young lady is walking on the beach. And now you tokenize these words. So you use word tokenize of this sentence. So for each of the words in the tokenized words, this contains a list of all the words as tokens. So, and then you do POS tagging, NLTK.POS tagging for all the tokens. When you print that, you see it has performed the POS tagging for each of the tokens over here. It is run a tuple of the given word, comma, its POS tagging. So this is the application of POS tagging. Now this word cloud. Okay, so the word cloud is a very cool application for the frequency distribution. You might have come across this in other applications as well, I'm sure. So from word cloud, we import word cloud. So this and we use a matplotlib to plot this. Okay, so this is for to plot the graph. So word cloud dot generate text. So it takes the text as the input. The initial text we had actually read from the GitHub website. So it takes that text as the input, and so that'll be the word that'll generate this plot. So plt.figure, you figure size is this. You give the figure size and you show this image. plt.im show the word cloud. It displays this as the image. plt.axis off, because do not show the axis over here. Right? plt.show, it actually displays the image right here. So here mainly what is the words which have larger font size have larger frequency in the given text. Say pig occurs many times compared to the word, let's say, enough over here. So this is one of the applications of that. Next, let's see word embeddings. Okay, so firstly, bag of words. So from sklearn or feature extraction.test, there is a count vectorizer. Let's see what is this function. First, let's create a corpus, or say text data. These are the sentences. All my cats in a row. When my cat sits down, she looks like a Furby toy. Right? These are the given sentences. So you initiate a function for the count vectorizer. Vectorizer is equal to count vectorizer function. Now, so its corresponding bag of words matrix will be, so you just fit, you transform this using the function vectorizer. So you pass this text, the corpus, through this function, and you print its corresponding bag of words matrix. So here this is the vocabulary of the vectorizer. So all is 0, in the sense the 0th index represents the word all. So here cats 2. So this means the second 0, 1, 2. So this index right here represents the word cats. So this is what it means. This is a simple word bag of words matrix for the given corpus. Right? Okay. Next is TF-IDF score. So we'll use the same corpus from the previous implementation to get the TF-IDF scores. So again, from sklearn or feature extraction.txt, there is a TF-IDF vectorizer. We do not have to implement the algorithms for each of these, say count vectorizer, TF-IDF vectorizer, because there are built-in libraries which you can directly import and use. So vectorizer here, you initiate it with the TF-IDF vectorizer, and then you use the fit transform method to actually train it to perform the TF-IDF factorization on this. So when you print, you print the feature names and its TF-IDF values. So these are, in this list, so this is the order in which the TF-IDF values are being printed. So for the corresponding words, all, cat, cats, etc. So these are the sequence of words for which the corresponding TF-IDF values are represented here. So for all, it is this. And then for cat, it is 0. For cats, it is this. This is one. This is one list over here, as you can see. So this is for the first. This is for the first sentence. So similarly, for the second sentence, third sentence, fourth sentence. So this is the entire matrix that way. So this just converts. So this function x.toArray just converts it to an array. Okay, next is word to vec. The most interesting ones. Okay, so here we import the necessary libraries. We import string, NLTK. We import brown. Brown is another. It contains data. The data which we actually download, which we can use it, which are already trained on word embeddings, which we can use it for plotting and understanding the concepts. Okay, so gensim, from gensim.models import word to vec. Word to vec, that is the word to vec word embeddings. We import BCA as well, and pyplot to actually plot the graph. Okay, from nltk.download, we download brown, which is a brown. It's a corpus collection of documents which contains data and information. We process the brown corpus first. So document will be this brown.sentences. So this takes this generates a list with all the sentences. Okay, so this piece of code right here. Here, it appends all the sentences to an other list. So this is the new sentence for word in these sentences. So you perform lower casing for all the. This is basically for the corpus we have imported here. It is doing data preprocessing, text preprocessing over here. This part of code. So you remove the punctuation, you perform lower casing. Right. Now you train the word to vec model, retrain the word to vec model. So you initialize the model with word to vec. So the sentences so the data is taken as the input. So the vector size, you can define the dimensionality. So this is the window, the context window here again, and epochs for how many epochs it needs to train. So this will train based on that. So the vector love, so model.wb love. So this will print the vector for love, as you can see. So this is the corresponding vector for a given word, say love over here. So its dimensionality will be 50. It will contain 50 elements because we have given the vector size is equal to 50. Yeah, similar. Now we use this there are different applications of this as well. So we can use this to find the most similar words to car. Okay, similar to car, model.wb, most similar car. So it takes the word car as the input, and this is one parameter. Again, top n is equal to 3. So this means it gives the three words that are most similar to car. Right, the three words similar to car will be boat, truck, roads. If you change this, changes to 2 or 4, it gives you 2 or 4 words correspondingly. Right? Okay, so this visualizing data with PCA, this part of the code is to actually plot this right here. I won't go into details. It is just to plot it. So as you can see, when you plot these words, the graph. So France, India, Germany, they have similar meaning and similar context. So they're placed close to each other. Here, boat and truck, they almost overlap each other. So they're placed close to each other. So this is road placed here. So student and teacher, they have similar meaning and similar context. So they're placed close to each other. So this is a representation of the word embeddings in a two-dimensional vector space over here. Okay, so here based, as I had mentioned about the word relationship, between different words. So using that concept right here, we will find the capital of different countries given when one of the capital is given. For example, say finding capital of Britain, given that the capital of France is Paris. Okay, so this is using the vectorical representation. So as we saw in the image right there, you can. So the vectorical representation for the capital of Britain would be the vector France minus, the vector Paris minus France plus Britain. So this would give you the vectorical representation of the capital of Britain. So in this case, when you print it, okay, so this Google News vector, it just downloads the data from this and it loads the data and text from there. So when you print the capital of Britain, you get London over here. Okay. Yes. Next, similarly for India, you can do that for India as well. India. Yeah, when you do it for India, you will similarly get it for India as well. Here you can see similarly for Japan, you get Tokyo, right? For Italy, you get Rome. When you do this, okay, they're different. Now we see one more application is finding the three most similar words to beautiful. Say here you do words is equal to Google News vectors dot most similar beautiful, comma top n equal to 3. That is the three most similar words to the word beautiful. So here you get gorgeous, lovely, stunningly beautiful. So these are the words. Okay, so before this, there was five words similar to BMW. As you can see, so Google News vectors dot most similar BMW, comma top n equals 5. So here you get Audi, Mercedes, Benz, and these are its corresponding. So this numbers right here are the dot product of this vector with the vector BMW. So this is the cos value. Sorry. So as you can see, these values are pretty high and closer to 1, as you will observe, because they're placed closer to each other in the vector space. Yeah. So this is to find the cosine similarity between these two words, say fight and battle. So it's cosine value. So you do Google News vectors dot similarity of these two vectors, these two words you want to find. So its cosine value will be 0.7, because fight and battle are somewhat they mean the same thing. So words with similar meaning are placed close to each other. Whereas for words such as say fight and love, they're opposites of each other. They're antonyms. So you can see here its cosine value is much lesser, which indicates that they are placed far away from each other. Okay, so that's it. We're done with NLP basics. Now Anirudh will take over from here.
Yeah. So hi again. I'll be continuing with what Deveshi finished with by explaining RNNs, which is it is mostly used to carry on NLP operations. It is one of the models most acquainted to what Deveshi just taught. So yeah, just give me a second. Yeah. So yeah, we'll start off with RNNs and some other related topics. So we'll be going through RNN basics, its intuition, its architecture, forward passes, backward passes, its drawbacks, because even it's not a perfect model, and solutions that we have come up with for it. Then LSTMs, what they are, how they work, how they are better. And then we finally go to a very brief introduction to encoders and decoders, which are state of the art, and they are the ones mostly used nowadays. So yeah, first of all, what exactly is an RNN? Now, before getting into this, I want to tell you why we introduced something called RNN. Like, what was the issue with, what exactly was the issue with our normal neural networks that we used? They were also giving us outputs. They had a hidden state. They were carrying out everything perfectly. They took in words as tokens and then they processed that and they gave us inputs. So, what exactly was the problem that we were coming across? So, the problem was when we have one sentence, a regular neural network would just take in every single word independently. So even if we jumble the sentence of a bit, the RNN would still consider it to be the same. For example, look at these sentences. Like, you don't have to be well to travel with. If I'm bad, you're my dad. Like, doesn't make sense, because there are mild changes between where the words are placed that completely destroys the meaning of the sentence. So for this, we needed to invent something which would take up the semantic relationship between each word, where they are placed in the sentence and what's their alignment to other words. And consider even that while processing the information and give us an output accordingly. Otherwise, we would just be stuck. For example, if we gave these sentences to a regular neural network, it would just give us a generic output as always, even though this information practically does not make any sense. So yeah, so we'll come to what exactly RNN is. So RNN is basically just an improvement to regular neural networks where each new hidden state that we generate also takes into account the previous hidden state. It also takes into account what previous information we have already stored. Not every single input that it takes is independent of each other. This helps it to like make sense of a sequence. When we give it information in a sequence, it is able to capture the relationship between each different inputs. So yeah, then after this, once this is done, so yeah, as you can see, there's a little jumble in the words which made the entire sentence incoherent. So we cannot predict any reasonable output from this because we need a network which has access to some prior knowledge about data. That's what I said. So yeah, this is done. Then yeah, so this is basically how an RNN looks. Now the left side is a regular neural network where we have an input. One weight is multiplied to that. It passes to a hidden state. It gives an output. But in an RNN, we have the hidden state looping inside itself. It takes into account its own information in the next time step. Like every single time step will also include the information stored in the hidden state from the previous time step, which will help us know what had happened in the previous time step and how our output has to change regarding what has happened before. So yeah, so as you know, as you would have learned earlier, our regular hidden state is just Wx plus D, weight into input plus bias. But now here we have another term called weight, which is the previous hidden state multiplied by a corresponding weight, which again gives us the information that we want about the previous time step, which would help us in giving a better output. And this is put inside an activation function, which can be tan h, value, sigmoid, whatever, depending on what our needs are. And then this is finally multiplied to another output weight and added to a bias and passed through the softmax function, which would give us a probability distribution. And that's what our output is. So here the hidden state HT takes into account both the input sequence HT and the previous hidden state HT minus 1 and gives the corresponding output YT. So yeah, now we come to the architecture of these RNNs, how they exactly work. So to explain this, let me take an example. Suppose just take a word dogs. Let's just take a small word, no confusion. So when we input this to an RNN, first, if we give it the input letter by letter, for example, I'll first give it D, then O, then G, and I want it to predict S. I'll just give it 3 letters. I want it to predict the fourth letter. So suppose I give it D. This is time step 1, the first step we are doing, and I give it the letter D as input. Now it will process it and it should be giving O, but then it won't, because now if I have just given it the letter D, there are a million words from D, so it doesn't exactly know what word I'm expecting. So yeah, this O is just the ideal answer that we want, but then that's not the case here. It could be anything. But then when we move to the next time step, when we give it the input O, the second time step, now it is still going to remember the D that we have given it before in the previous time step, because that's what a recurrent neural network is all about. So now it has 2 letters in its memory, D and O. Now it has somewhat of a better idea of what word we have to predict. Although there are a lot of words, but then it's getting closer to what we want. Now for the third time step, I give it G as an input. Now it has a complete word, D-O-G, dog. It understands that we want something that would complete it. So now it can very easily predict S, because that's the only letter which appended to these 3 letters would make complete sense. And that's how a recurrent neural network fundamentally performs. And that's what its architecture is exactly. This is just the forward and backward propagation that you might have already seen. I'll just explain a bit about its skill. So the first, once we put in the input, usually we see WX. I've not included bias here just to avoid confusion, but yeah, that would also be always there. So, but since we are using a recurrent neural network, it would be WX plus WH. And that would give us the first hidden state value. Now this goes through an activation function, tanh, then it gives us some values. Now these values are multiplied to the output weights and passed through the softmax, as I said, and that gives us the output. And backward propagation you would have learned in earlier classes. It's just differentiation of the loss to optimize the function better. So we use a loss called multi-class cross entropy loss in this case. No need to get much into that. So it looks like this. This is the formula for that. And this is just the back propagation that you have learned. Nothing different for it. It's just we just have an extra term in the forward propagation and its own back propagation, respectively. So before diving further, I just want to ask, what exactly is the issue? Like, we have such a great system, it's able to remember stuff from before. So why do we what's the issue? This is a question for you guys. What is exactly the issue that we are facing even with RNNs? And yeah, this is a hint. The activation function Sigmund and tanh also face the same issue. Yeah, so someone said vanishing gradient issue. So yeah, that's precisely the answer. So what exactly is the vanishing gradient issue? For example, just take this sentence. The brown and black dog, which was playing with a cat, was a German Shepherd. So here, for example, if we give part of this sentence as to the model and we want it to predict German and Shepherd here. Or like if we ask it, what was the color of the dog? What was the color of the German Shepherd more like? So if the model back propagates, brown and black is quite far away from German Shepherd. So while traversing backwards, while going from word to word, if many gradients have the values less than 1, so the multiplications would eventually come to a value which is very close to 0. And that would practically mean that we have lost no gradient. and the model just stops learning. Since the gradients cannot be updated further because it's just going to 0. So because of this issue, now the model cannot tell us what the color of the dog was or what the color of the German Shepherd was. So to evade this problem, this was why RNNs are not in use nowadays, because RNNs cannot exactly work for a long sequence of inputs. It's good for small inputs, but then if we give it a very long input, very long sequence, so it stops working. So yeah, as you can see, this is the chain rule for the backpropagation. And as you can see, there are so many terms in this, so many multiplications. So if even half of these are less than 1, so it would finally go to 0. So yeah, that the solution that we came up for this issue was LSTMs, long short-term memories, which basically account for this vanishing event issue that RNNs face. So this LSTM basically, the core concept of LSTMs are the cell state. A cell state is like a highway. This model, LSTMs, has a big highway which connects all the gates. Now there are 3 gates in LSTMs: the forget gate, input gate, and output gate. We'll come to these in some time, but these are all connected to each other through the cell state, which basically acts as a highway for all the information to pass through. So yeah, the cell state, the forget gate, the input gate, and the output gate. So we'll go to the forget gate. Now, what exactly is the forget gate? Now, this basically consists of a sigmoid function. This wavy line inside the orange circle is a sigmoid function, and the blue circle is the tanh function. So in the forget gate, we have a sigmoid function, which basically helps us to forget some specific data in vague terms. Like if we have a huge amount of data, so the sigmoid function would give values close to 0 to the information that we don't need, and values close to 1 to the information that we need. So that effectively helps us in segregating the data into data we need and data we want to discard. And yeah, so whichever information has values close to 0 multiplied to it would eventually vanish, and the data close to 1 would just be propagated forward. So that's what basically is the function of a forget gate. So as you can see in this animation, the previous hidden layers, the information and the new input is going to the sigmoid function, and the value that we have remembered goes to the cell state, where it is pointwise multiplied to the existing cell state. Now, what is pointwise multiplication? That means that if we have 2 matrices, so pointwise multiplication means the multiplication of every single index to each other. For example, if we have 2 matrices 3 cross 3, so the 1 1 place would be multiplied to the 1 1 place of the other matrix, and so on. So like every index would be multiplied to the same index in the other matrix. That's what pointwise multiplication is. Then after this, we go to the input gate. Now the input gate is basically, it takes in all the input that we need from the new information that we have. So we have another sigmoid function here again, which works in the complete same way as the forget gate works. And we also have a tanh function here, which gives the information values between -1 and 1. So this effectively helps us into determining whether we want to remove the data or add the data in the total corpus here. So the tanh function, yeah, so we can either remove or add data, and then these get the sigmoid value and the tanh value also get pointwise multiplied, so that the value that we have got from the tanh function, the value that we want to remove or add, also gets to know which information needs to be forgotten. So that basically optimizes the model more. So now instead of worrying about 100 things out of which 50 we have to remove and add, if we have forgotten 50 elements that we don't want, so we just have to deal with the other 50. And now this new input, after going through this, is added to the cell state, which is going on from the previous time step, which has already been multiplied with the forget gate value, so that stuff is forgotten from there. And now it's added to this new information. That's basically why this is called the input gate, because it adds more input to it. And this plus is also again the pointwise addition. Pointwise addition works the same as pointwise multiplication. The only difference is it adds stuff. Now, after this is done, we'll come to what happens in the cell state. So, like I've said, it first gets pointwise multiplied with the forget gate, pointwise added to the input gate, and then it finally goes towards the output gate. The information first of all goes directly to the next time step cell state, and it simultaneously also enters the output gate. So the information goes to the next time step because we want this cell state to be as it is for the next time step. But it also enters the output gate so that we can update the next hidden layer. Because again, since we are in an LSTM, two things matter to us: the updated information and the updated hidden state. So after this, we'll come to the output gate. So the output gate is basically the last part of the LSTM where again, the information that we have, the input and the previous hidden state would go through a sigmoid function, which has the same purpose as it had earlier. And the cell state that we had would pass to a tanh function, which again has the same function it had earlier to either extract or add data. And again, these get pointwise multiplied so that we can optimize the model. And this is the new hidden state that we have. So now we have two values, the cell state that goes forward and the new hidden state which also goes forward as the next hidden state, which will again be used with the next input for the same function. So that's basically the core concept of LSTM. But there is a problem even with this. Even this is not perfect. We still face a lot of issues that even LSTMs can't cope up with. For example, if I have any sentence in English or some other language, and I want to translate that to some other language. For example, if I want to translate hello to Chinese, as I've written here. So in Chinese, let me tell you, it's ni hao, which is 2 words. But these LSTMs and RNNs, they operate on fixed lengths. We have a fixed length of input, we get a fixed length of output. So if I just give it hello, it won't know that in Chinese it's 2 words, and it would just fail to perform. So that's where we come across sequence-to-sequence models, that take inputs of any size and then compress them into a single vector. It takes all information of all sizes, finally compresses them into one single vector, and this is given to another model which decodes this, and then it gives us outputs of varying lengths. So I'll just go very briefly over this. So yeah, the sequence-to-sequence models is basically, we will be going through encoders and decoders. Now, what's exactly an encoder and what's exactly a decoder? So an encoder is basically one RNN or one LSTM, which takes in values of different lengths, and the final values that it gets, the final output, is one single vector called the encoder vector, which contains all the information that it has got through inputs, hidden states, and all. And this is gone to another LSTM or another RNN model called the decoder. And this decoder helps us to gain the output that we want. It converts those numbers back to meaningful words and sentences that we want. That's what encoders and decoders are. So yeah, encoder and an RNN model which accepts a single element of the input sequence, collects information for an element and propagates it forward, gives rise to the final encoded vector, which is the final vector that we get. So yeah, its formula is the same. Any activation function, inside it, we will have weight into previous hidden state plus weight into the input that we have. The encoded vector is the final hidden state produced from the encoder part of the model. It acts as the initial hidden state of the decoder part of the model. And yeah, a decoder predicts an output yt at a time step t. Now each time step accepts a hidden state from the previous time step, which is exactly how an RNN or an LSTM works. And it has its own hidden state. And the output yt at time step t is computed using the formula yt is softmax of the output that we have, w into h. So yeah, that's practically what I wanted to teach in RNNs. So let me know if any of you have any doubts, or we'll move forward to the quiz that happened. Any doubts?
అమ్మా పోనివరా వచ్చేసింది ఎంత ఎక్కిందే
What do you mean exactly by normal function? Someone has texted. If you are talking about F, by which I mean the activation function, that basically helps the network to know which inputs have to be used and which to be not. F, yeah. But softmax is just a function that gives us the probability. Like if I have 10 in outputs, what's the probability of each of them to occur? That's what softmax does. That's not exactly.
ఎవరికైనా చేసేస్తావేమో అన్న భయమే కాదు అక్కడ
Yeah, that's what basically the difference between activation functions, which is F, and softmax is, because activation functions are basically helping the neural network to determine which of these inputs have to be used now and which have to be not, which is not what softmax does. So I hope I cleared that. So we'll go. So we go we will not exactly be covering attention here because that's quite complicated relating to what we have exactly learned here. So let's not exactly get into attention for a time being. But yeah, if you want a very basic understanding of what attention is, it's basically here how we are using, how the entire model, it's sequential, right? We have one previous hidden state, now we get a new hidden state, we get another new hidden state after this, and so on. Now in attention mechanism, what it does, it parallelizes all the hidden layers. So at every time step, we have all the other time steps along with that, with us, so that we can take up information from any hidden state at any point of time. So I don't need to worry that when I'm updating the hidden time step, there can be a case that I've lost something. So that's what a basic idea about attention is. But I'll be sharing the quiz now. Give me a second. Just scan this QR code and you'll be able to join. I'll start off in another 15 seconds, so make sure you join before that. Yeah, let's start. So yeah, well done. We'll go off with the code implementation now for RNNs. So yeah. So basically the data set that we would be working with is basically the names of certain languages and all the names associated with them. So we have Chinese, we have Greek, and we have all the names that the Greek people or Chinese people usually keep. For example, we have Edward, John, and stuff for English, and so on. So we have a so the data set that we have, we first need to bring that data set to our code. We want to import it. To import that, we have imported certain libraries called open to open the file, globe to access the global file from wherever it is, and OS. So we first define a function called find files, which will return the path of the file that we want after completely searching the computer, which is what globe, GLOB does. Then we print it, and then we unzip it, because since the data set that we have is in zip format, we have to unzip it to use it. Then we import two more libraries that we will have a lot of use of, and then we'll start off. So first of all, we have to define a variable which will contain all of these letters and some important punctuation marks along with them. So first of all, what is ASCII? Now ASCII is basically all the letters and their capital forms in base format. We don't want diacritical marks and stuff like that, and non-ASCII characters. Now, what are diacritical marks? Now, for example, have you heard of the word cafe? So now cafe, the E at the end of cafe has a small mark over it. So marks like that are called diacritical marks, and we don't want them. So to remove those and to remove non-ASCII characters, some other characters which we do not consider in ASCII format, we first need to convert the string to string.ASCII letters, which will only have the 26 letters that we have and their capital forms, plus space, full stop, comma, semicolon, and apostrophe. All of this will be constituted in all letters. And n letters will be the length of all letters, which is 26 plus 26 plus 5, which is 57. Now if suppose we get some word which is how does it has diacritical marks, it's not ASCII. So first of all, to go about with it, we need to convert it into ASCII. We need to convert it into the ASCII format that I have just defined. So to do that, I define a function called Unicode to ASCII, where this function basically just converts all of those letters which are non-ASCII to ASCII, if they are able to do that. Otherwise, it will just remove that. So NFD is normalization form decomposition. S is just the the parameter of the function which we need to decompose, and NFD basically decomposes all the letters with diacritical marks into its ASCII format. If Unicode data category C not equal to MN, MN is just diacritical marks, then we have to disconsider that. We just want ASCII letters. And then let's suppose, so this is what I'm talking about when I'm saying diacritical marks. You see these small lines over A and over S. We don't want that. We can't work with that. So we need to convert that into ASCII format. So when I use this function and print that, I'll get something like this, which is just the ASCII letters that I need. Then after that, it's just we just define another function, read lines, which will basically help us into segregating the dataset into the countries and their names. We define a list, all categories, which will hold all the languages, and category lines as a dictionary, which will have the key as the name of the country and all the names of the people like relating to that language or country below it. So these curly brackets denote a dictionary and square brackets denote a list. Now read lines will basically just demarcate both of them, countries separate and names separate. And for file name in find files, this basically will get us the dataset, and we create a category called overs.path.split text, overs.path.base name file name. Now this will basically just, again, this is the same thing. We just need to demarcate both of them. So all categories we will append a category so that all the countries come under all categories. And lines is basically the function that we have defined, read lines. And I use that on file name, which is our dataset. So this will give us all the names of the people of that particular language. And I'll add this to the dictionary that we have, category lines. So now when I print both of these, and n categories is just the length of all categories, which are the languages. So now that I print both of them, all categories will basically give me a list of all the languages that I have, Greek, Portuguese, Russian, etc. And category lines would give me all the names of one particular language. So for example, as you can see, it's Polish. And Polish, the names start alphabetically and goes on to Z. And then we have a new language, Chinese, and then similar. Once this is done, so print, I just want, like, for example, I just took first five names of Italians. So that gave me 5 names starting on A, because of course it's alphabetical. So the first names would always start from A. Then we'll go to another part that we have to do here is, now that we have all these in letter format, now we can't exactly give the model all these information in letters, like it won't understand what you're saying. We need to convert it into specific numbers, which it can understand. So to do that, we have defined a function called letter to index, which will return all the letters dot find letter. For example, if we have a set of all letters called all letters, so if we want A, that would be at the 0th index. B would be first, because again, indexing here starts from 0 and not 1. So A is equal to 0, B is 1, and so on. So now that we have defined this, we use this in another function that we have defined called letter to tensor, where the tensor we would first initialize as a 0 tensor, all zeros, and then we will turn that particular index to 1 where that letter stands. For example, since we For example, like since it's just the matrix 1, n letters, so it just has one dimension. It has two dimensions, one of which is 1 and the other is the size of total letters. So 0 will denote, because since it's only one row, so or one column, however you may assume it to be. So 0 will be, so one of them will always be 0. Since like for example, the first index would be 0, 0. So since we only have one column or row, one will always be 0. And the other would be the index where we want to change it to 1. So here we would use letter to index and we'll put the letter that we want and change that to 1. For example, if we want to convert the letter J to a vector, so I'll use letter to tensor J. And as you can see, since it's a capital letter J, so first we will have all 26 small letters. And then since J is a 10th letter of the alphabet, the capital J letter would have a 1 at the 36th point of the tensor. So as you can see, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36. So this is at the 36th place. So yeah, that's how you do it. And suppose you want to convert an entire word to tensors, like if you do one tensor, like we are just dealing with letters now. Suppose we want to convert an entire word to that. So to do that, we define another function called line to tensor, where again, we do the same thing. Tensor is going to toss out zeros, but the length of the line, 1, 10 letters. Now we have 3 dimensions. And length of line would be the length of the word, like how many letters it has. So for example, if we take Jones, length of line will be 5. Len bracket line will be 5. And this is practically the same thing that we have done above. And yeah, so we will get, and since we have 5, we have to use a for loop so that for every letter it does the same function. And we will return the tensor accordingly. As you can see, the shape of the word Jones is 5, 1, 57. Yeah. Now after we have done all this stuff on the data, we'll go to our actual RNN model. So now the RNN model, as we already discussed. So first of all, we initialize the constructor. We create the weights. So the input weight, the hidden weight, and the output weight. Then the softmax function, which is here I've used a log softmax function, which is basically just the log of the values that we get as probability. So nothing else. So whatever values we find at the end, when we predict the answers, whatever values we have, we just have to raise that to the power of e raised to the power of that value, and we'll get the probability respectively. And we also define hidden size in the constructor. Now after that, we go to the forward pass. So forward pass will take in the weights which is defined with a self function, self parameter, input, which is the input that we will give it, and hidden is the previous hidden state. So hidden here, I'm using the functional library that I exported. So to use the tanh, I do not need to define the tanh function. I could directly take that because PyTorch gives it to me directly. It wants to make my life easy. So I have imported neural network from Torch, and I've imported functional from the neural network that I imported from Torch. And I use that to form the hidden state that I want, tanh of wx plus wh that I've said. And output would be the output weight into this hidden state, and then after we have calculated this, we will put that through the softmax function that we have defined earlier to get the final values at go. And this is just another function which we can use or cannot use to initialize the hidden state. So in some places I have used it, in some I have not. Doesn't matter. So it will basically just give us a tensor of 1, the hidden size that we have defined, and all of the values inside the tensor would be 0, and that would be changing as the neural network processes the data. So n hidden is 128. So the number of neurons in the hidden layer, I have defined it to be 128. And RNN is just a small RNN is just a variable that calls this class with these 3 parameters: n letters, n hidden, and n categories. So the input size, hidden size, and output size. Now I just, for example, I just define input as letter to tensor of A, just the letter A, and hidden as top zeros dot n 1 comma n hidden, which I could also have done calling this function init hidden, or I could just directly define it as follows. And then I want the output and the next hidden state that I would be getting from this. So I pass these two, this input and hidden, through the RNN that I formed. So now this will give me some values of inside a tensor. And similarly, if I want to convert this word Albert into a tensor, so now it will give me 2 dimensions, like 3 dimensions. So it would be, the hidden would be dot 0, 1 comma n hidden, obviously. And the output comma next hidden will again, I'll put it through RNN, through the RNN that are formed and print that accordingly. So now it will give me the values relating to each. That's what this practically is. So now after this is done, this is just to print, just to give an idea. Now that is done, we'll define another function for category from output, which will give us the highest value and its index from the tensor that we are getting. For example, here it's this, -3 is the greatest. So it will give me the index and the corresponding name of the language to that in my data. So here's it's the Japanese at 8 is technically for this, the first one. It's not relating to Albert because again, no Japanese guy can be ever named Albert. This output is for the previous one because surprisingly, Japanese people also have single letters as their names. So once that's done, so the value, the highest value that the letter A has in its tensor is the index 8. And it's, yeah. Now after that, we import the random library so that we just take some random words, some random languages and names relating to the language from our entire corpus. So defining, so here I added a lot of comments to just help you guys along with it. So random choice is basically to choose a random element from the list. So here the parameter is L. So afterwards I put the country or language category inside this. So this will return L random.randind 0 comma length of L -1 because since it starts from 0, so it has to end 1 before the full length. So if it has a length of 10, it would go from 0 to 9. And it would take up the value at that particular point of the list. So for example, if this goal comes out to be 8, so that would give me the 8th value, like the list, the name of the language at the 8th position of the list. So random training example is another function that we define where the category is just like we initialize a new variable called category, and that would be a random choice from the all categories, the entire list of the languages that we have. And this would be just one random out of them. And line would just be one random name from that country. So again, we use random choice for the same. The category tensor would just be changing the category to a tensor, as we have seen, and line tensor would be changing the line to a tensor because again, the model cannot use words, it needs numbers. And we would return all these. And then here I'm just using the for loop to print all the values that I'm getting. So category is Spanish, line is Jaso, and I'll be getting the tensors for both. So after this, I define my loss function as nn.nll loss, which is one loss that we'll be using here. Then learning rate, I define as 0.005 because I don't want to take the risk of keeping the learning rate too high or too low. So this is basically something that we just have to test again and again to get that final perfect value. And then I define the train function. Now the train function, first of all, now here I've defined the hidden state using the function init hidden. I could also do it using torch.zeros, but I just chosen to do it like this way. RNN.0grad would just initialize all the gradients to 0. I don't want any redundant values of the gradient hindering my progress afterwards. So for I in range, line tensor dot size, I'll be getting output and hidden for every single letter back to back. Therefore, the for loop. And this will be for the input, which is the line any one letter of the line tensor and the previous hidden string. Now the loss would be just the criterion that we have defined, and I'll be putting the output and the target output, the category tensor, the actual name and the predicted name. And I will be finding what the loss is and how I have to optimize it accordingly. And then this is just the backward pass that we do, back propagation. This would help us in optimizing our model. And then after that, usually we use a function called optimizer.step. Here I've just used something different from that, but it does the same job. For p in RNN.parameters, p.data.add, p.grad.data, comma, alpha is equal to minus learning rate. So this is basically just adding the parameters gradient to the values, which is what we do in optimizer step. And then this will go back to the for loop, and then we'll be getting the same, we'll be getting the updated values accordingly. Now, after this is something that's not much needed, but then we just want to find out what, like how much time every single epoch has taken. Not every single epoch, a set of epochs that we have taken together. So for example, here, print every is 5,000, for example. So print every basically tells me to print the output every 5,000 epochs. So after every 5,000 epochs, I'll be getting the time taken for the epoch, 5,000 epochs to occur, and the value of the loss and the accuracy that I've got. And plot every is basically another variable that helps in just plotting. If I want to plot a graph, it would just help me in doing so. But this says that I have to do it after every 1,000 epochs. And num iterations is basically the number of epochs that we want to run. That is 1 lakh here. Current loss is 0. All loss is the list that I've created. I will be adding the loss into this back to back. So now this is the time function. So basically here, I define a function called time since. This will give me the number of minutes and seconds my model is taking to run 5,000 epochs. So time.type parenthesis will give me the current time. S is basically the number of seconds. So number of seconds would be the time now minus the time when I started. So if for example, now it's 7 o'clock, I started at 6:59. So the number of seconds the model has taken is 60 seconds. And M is the minutes, which I just divide S by 60 to convert that to a minute. And then I update S in such a way that it removes all the minutes from it and just gives me the remaining seconds. For example, if I have 3 minutes, 44 seconds, for example. So when I divide that by 60, I get a remainder of 44. So that would be my new seconds. So it will give me a value of 3 minutes, 44 seconds. And I just asked it to return that in this format, X minutes, Y seconds. Start will just start the timer. Then for iterations in range 1, num iterations for +1, as we have started from 1 and not 0. So I wanted to give me the category line, the tensor for the category and line tensor from the random training example that we have defined here. This, and after that has happened, we'll be wanting the output and the loss using the train function, and we'll be adding that to the current loss that we have defined from here. So after this is done, we want to print it after every 5,000 epochs. So I'm saying if iterations divided by print every leaves no remainder, so I will be wanting guess and guess I, which are 2 new variables that are formed from category from output, the function that we have defined earlier, when I give it the output that I've got. So output is what we get when we train the model. And this, when we put inside the category from output, we'll get the name of the language and the index where the value was maximum, as we had defined earlier. And that would, so index of the guess and the guess, this is what we'll be getting. Guess I is guess index. And this now I'll be putting a tick after every single correct prediction, and not prediction exactly, of correct guess, and wrong after every wrong guess. And I would print that accordingly. So I'll get something like this. So 5,000 May, for this name, it said it is Polish, it's correct. For this, it said it's Portuguese, it's wrong, and so on. And I get the time taken for it accordingly. Now, this is something that's not exactly relevant to this code, but then I just did that to get for you guys to get a better idea out of it. So I won't be going much in depth over this, but this is just the confusion matrix. We have created a confusion matrix. Now, what exactly is a confusion matrix? It will list all the names of the languages in the X and the Y axis and give me the probability as to how much both the values are matching. For example, I'll directly show you the probability, the confusion matrix. So here, yellow is best case probability 1 and 0 is lowest. So when Greek and Greek come together, it's yellow. That means it's predicting every single Greek name as Greek only. So it's good in that sense. Even for Portuguese, it's yellow. For Russian, it's slightly green. So I can see that it's not that adept at guessing Russian names. For English, it's a bit too low. It's around 0.3. That means it's not able to predict English names at all. But as I can see, English, the line English has a lighter color near Irish. That means the model has a 0.4 probability of predicting English, of guessing English names as Irish, which makes sense because there a lot of names are similar among them. And you can see some problems. For example, let me take Japanese. And Japanese, as I can see, or I will take Korean, for example. So I can see Korean has somewhat of a light color next to Chinese, which again makes sense because their names are very similar to each other. Even Japanese is having somewhat similarity with Korean because they have a lot of similarities between their names. So that's what basically a confusion matrix does. It gives us a fair idea of how our model is working. So it's basically, I just evaluated the model. I wanted to make predictions now, so I put it into evaluate mode. And I defined a confusion matrix. I put all these values inside that. You can go through all of this once I send you this code. And yeah, PLD show will basically show me this matrix. And after this is done, we'll finally go towards actually predicting, actually gauging the predictive power of our model. So let me just take some 3 random names, Noveski, Jackson, Satoshi. I'll input that into the predict function, which I have defined over. So predict will basically just, predict will give me the log of the softmax, as I've said, of what language it can be. So the probability of it being Russian is e raised to the power minus 0.92. Czech being minus 1.4, e raised to the power minus 1.49. English being e raised to the power minus 1.99. And that would give me the probability of the name being out of either of these 3. And yeah, so again, for Jackson, it will give me 3 values. For Satoshi, it will give me 3 values accordingly. That basically brings us to the end of this code and the end of this topic of RNNs. So if you have any doubts and any problems with it, you're free to ask.
తుంగమంట కొడుకులు ఇంకా అటెండెన్స్ లింక్ బెట్లా చూసేసిన ఏం లేదమ్మా
The session is end. Give me a second. I'll just share the screen with the attendance link, so that would be easier for me. Yeah, this is the attendance link. You can just scan this to get the attendance. for people who are attending through phone itself, the attendance link has also been shared in the chat. So yeah, you can use both. And if you don't have any doubts, if you are completely clear and if you have done the attendance, you are free to leave.